Okay. All right, so we've made it to the last day. Woohoo! I'll have more comments right at the end of class about what this class, where you should feel that you are after taking this class and so forth. Without raising your hands, unless you absolutely want to, how many people in here came into CS 110 and went, oh man, CS 110, I've heard that it's so much work and it's going to be yeah, I see a couple people going, all right, I don't mind telling you it's going to be a lot of work. But it's been okay, right? You've made it and you did very well overall. I think I'm very happy with the way students have done and how people have gone through the class. As I think I might have said before, it's not me speaking up here that's teaching you all this stuff. As much as I'd love to say, well, I'm the one teaching you all this stuff, it's you doing the assignments really is where you get the learning out of this, right? You don't learn about sig suspend from me telling you what sig suspend is. You learn about it from wait, how does this work and how do I program it? What's this weird race condition and why is my code stalling and why is there this deadlock and whatever. You learn that from actually doing it and putting in the hard work. So good job there. I'll have a couple more comments about that later. So how's the assignment going? MapReduce, getting there? Okay, some people are I haven't started it yet. You should probably start it soon if you haven't yet. Technically, it's due today. I put something on Piazza that said, look, somebody else answered this on Piazza that said that you won't have any late days until starting Friday. So you still have until tomorrow without any late credit for the assignment if you're still working on it. I will have office hours both today right after class for about an hour and then tomorrow morning my normal regular office hours, I will hold those as well. You are welcome to stop by and chat about the assignment or about the final exam and so forth. And the exam is Monday, so it's coming up pretty quickly. There's not actually that much time before the exam, but it's Monday. If you do have extenuating circumstances and need to take the later exam and so forth, please let me know before too long. If you have other accommodations, I will email you in the next day or two about timings and so forth. Okay? Yes, question, Hassan? Yeah, that's a good question. The question was, are there going to be any office hours over the weekend? We will definitely have something on Sunday. I haven't talked to the CAs yet about what other plans they do. But we'll have some. There's also going to be a review session that I think the CAs were talking about Saturday at some point or something like that. But we'll let you know as soon as we can about that. Yeah, so that's that. And then let's see what else. We will have everything graded midweek next week as best we can before that. As far as one other logistical thing for the end of term evaluations, please do that if you get the chance. I will gladly take any constructive feedback. And constructive feedback is oh, you know what, there was too much material or this material didn't make much sense when you covered it. And I mean, I'm not upset about good constructive feedback. Feedback the class sucked is not going to help you much, right? But feedback hey, I wish Chris would have done this, or this was good, but this could have been better, that sort of stuff, fine with me. I'm always trying to make the class better. So I'll appreciate if you did those. Let's see. Okay, so today we're going to talk about a topic that's not on the final. And in fact, I was looking at it, I was going over it this morning going, it's way too much for one lecture. This is actually too much stuff, so I'm going to skip some things in here and basically give you the kind of the overview with a couple of examples of this non-blocking I/O. So far, we have been talking about I/O, in other words, reads and writes, that when you do the system call for read or write with a file descriptor, it actually blocks until it gets a response, and the response is some amount of data. Now, it's not always all the data you're either sending or requesting, but it's some of the data, or at least it's going to be some data, and it waits until that some data is actually processed, be it over the network or reading or writing a file. And the way we get around those limitations is we have just been doing multithreading or multiprocessing, but generally multithreading, where we say, oh, great, we're going to have this read or write, but it's going to block. So we're going to have the ability for other threads to accept connections or to be also doing work. That's how we're getting around it. It's not the only way. There is this idea of having a non-blocking situation where you say, I'm going to read some data, and it might come back with 0 data, but it comes back instantly. Either it comes back with some amount of data, and we're going to see why that might be an interesting idea. And of course, you can't do it just on your own, in your own program. There's going to be some other things we need to have support from the kernel and from the operating system about. Yeah, question.
Sort of related to I/O and the practice final lab 4, the terminology of CPU bound and I/O bound. What those mean?
Yeah, good question. So this just came up on Piazza. There was a question on a recent file, maybe last quarter actually, that mentioned the term I/O bound, and we can contrast that with CPU bound. Okay, and I made a comment in the Piazza post, you should know what I/O bound means, and maybe we haven't talked about it explicitly, but here's what I/O bound actually means. It means that your processor is not chugging away doing calculations. It's just waiting for some input or output to happen. And that's this idea of this blocking sort of idea is it takes time for data to be processed. Now, I mentioned on Monday that when you're reading and writing from a hard drive, it's like millions of times slower than reading and writing from memory. And so there is some what we call latency that is involved with actually doing a read or a write. So something that's I/O bound means your CPU is sitting there twiddling its thumbs going, I don't know what to do right now because I can't go on until I get some data. So that's what it means to be I/O bound. CPU bound is kind of the exact opposite. It means that your computer is chugging away doing something and it can't finish some function until it finishes all of the calculations it needs to do or something that is taking the processor's time, right? If something's I/O bound, if you can use that processor, which by the way is really fast, to do some other work, let's do that. And that's where we have multi-threading, and that's why having this question came up the other day too, about, what happened when we had one processor? How did we get this idea of multi-processing, or multi-threading? How did that actually work? It was because your processor is so fast that it can switch between processes faster than you can notice, so that when you move your mouse around the screen, guess what? That's a different process taking care of the mouse movement, but you can't tell because it happens so fast and it does such a small amount of work that it looks like it's just happening at the exact same time as something else. And on a multi-processor computer, like the ones we have these days, it probably is, but on a single processor, it was just that your mouse would move around, and part of the time that it would have been working on your program is now spent actually moving the mouse and updating the screen and so forth. And this goes back all the way back to the mid-1980s when you bought the original Macintosh computer. It had mouse routines that it would look just like, something would be happening and the mouse would take over for a second and you couldn't tell that it was time from the processor to take the time. Yep. I mean, saying something is I/O blocked is similar, yes. I mean, the term I/O bound is well known as, you've got a processor that's doing some input-output, and it's bound by the fact that the slow part is the input-output. That's really what I/O bound generally means. And if you can make something CPU bound, that's not necessarily a bad thing. It's neither one of these is a bad thing, but being CPU bound is actually harder because your computer is so fast at doing things, right? Now, if you were trying to factor large numbers, yeah, that's going to be a CPU bound sort of thing because it takes a lot of processing to do that, right? And it might be that you have to factor some large number and then spit it out to the processor. So in fact, I guess the farm program that we did with multiprocessing had elements of it that were CPU bound on the Python side, right? Because it had to do all that factoring and then it never got back to you with a response until after the CPU part was done. So you can do that, but knowing the difference between these two terms is going to be helpful long term anyway. So yeah, question, Kathleen, and then we'll go back. Yeah.
So what are always be one of them, right? Because
Would a program always be one of them? A program could at certain times be CPU bound and at certain times be IO bound, but it's going to be one or the other generally. Yeah.
it's always going to fit into one of those.
It's generally going to fit into one of those. Although you could, if let's say you knew you were going to have a whole bunch of IO bound threads, just keep doing more threads until it becomes CPU bound, or the trade-off is not. Then that's perfect, right? You've got all these outstanding connections, and you're chugging away, creating all your processing all these outstanding connections, and you've got so many that it actually is taking your processor time until you get something back. So yeah, I mean the trade-off would be, or the idea would be, yeah, keep doing more CPU stuff while you can. So now. Sometimes you don't want to do that because it takes more energy and there's other things going on. Your fans are come on your computer and whatever. But if you really wanted to eke out every processor cycle from your computer, you would keep doing more threads to be able to do that.
And you said that this sort of terminology and thought process is final stuff.
Yeah, I mean, I could say, why is networking going to be IO bound, and you would have to say, oh, it's because it's the slower part of the connection and it's got to talk between two computers and it's not your processor has to wait, and we use sig suspend, and we use other blocking sort of reads and writes and so forth. So yeah. Other questions on that? Good questions. Okay, so let's talk about I/O in general and system calls. We have this idea that we have fast system calls. Okay, those are the ones that return immediately, which means all they need to do is do some process that doesn't really involve a connection or file reading or writing and so forth. So there are lots of examples of system calls that might do that, but let's say get host name or something like that. That system call doesn't need to go outside the network. It needs to just query something that the kernel already knows about. It just returns immediately, and that's the way it goes. There's no real limit on immediately as long as it needs to do stuff, as long as the processor needs to be doing things, or the kernel needs to be actually doing something to do that. That still can be considered fast. Even if it takes 60 seconds, it still might be fast because it has to do something. So you're factoring a whole bunch of numbers, or you're factoring one number, it might be still fast in the sense that it's not waiting around. But the idea of a slow system call is when it actually has to say, I can't do anything right now until something else responds to me or gets back with some data and so forth. Okay, so slow system calls are the ones where we don't know how long they're going to wait. It depends on some other resource, right? Reading from a client might depend on some other computer getting back to you, and we want to minimize that kind of behavior if we can help it. Okay, so calls to read are fast if they're from a local file, because it's not that much. But you still depends on what your definition is. You could still consider that slow because file reading is slower than memory access and so forth. But in general, it's relatively fast. Write calls are slow if it's going to a socket, or if there's some internal congestion, like the socket is filled with lots of ingoing and outgoing connections. And that can happen when you have one port responding to all these connections. Like a web server often has its port, like it's really on the edge of, oh my gosh, I'm almost going to not have enough time to respond to these because just the port itself is getting lots and lots of requests. This is what happens when you go online to like Reddit and somebody puts a web page and they're not ready for all the connections and it like suddenly goes down. It's because, well, I just couldn't handle all the connections. So we want to avoid that if we can. Okay? And then slow system calls in general can block indefinitely. In other words, you have to wait for them. And in that case, they're considered slow. We've done some of this before where we've made it so that slow system calls don't matter. Wait PID is a good one, where we have that no hang. Remember before when we said, oh, if we do wait PID without no hang and the -1, or not even the -1, just the no hang, it will wait until the child ends. And that's a slow system call because it's waiting for the child to end, and it just goes, oh, I'm just going to be off the processor until the child finishes. So once we start using no hang, you have some more logic you have to use, but it means that you can get control back and just call it again at some other time after you've done some other work, and then it won't, and then you get the benefit of not having to hold up until that ends. Okay, so let's see, read and write with IO stream. We've generally done it with multi-threading to say, great, do the accept call, but do it in another thread so that you can go back and do another accept immediately. Now we're going to do it in a slightly different way. Okay, accept and read slow the way we've been doing them. So we'll see. We're going to have to work up to this, by the way, about how this works. So how do we actually make these slow system calls fast? Well, we can tell the system, don't wait on an accept call. Well, what does that mean? It means you call accept and then it returns immediately, and you're responsible for doing it again if you need to actually get a connection. We'll see how this works. It's going to be a lot of while true loops with some extra help from the operating system, okay, as we'll see. And we've done some of this before in other forms, so it will look very similar in the big picture. So generally, if you do accept, if you set it to non-blocking, it can return with -1, which generally means an error, and often it sets, remember, it sets error no if you get an error. In this case, it sets it to E would block, which basically says, okay, it's the error is that it would block, except there's no connection to block on, so that's the error. So it's not really an error, but that's how you handle it. We've seen that before as well. Okay. Same thing with read and write. You can set those to be non-blocking, but then it becomes your responsibility to call them again when you want to send more data. Okay, now you already have to do that because all the data might not get sent from your buffer anyway, but in this case it could be 0 bytes get sent just because it's not even ready to take your request at all, so it just returns immediately, and at some further time in the future it will send the data. Okay, so if there's no more, if it would block and there is data to be sent still, you'll get this -1 business back. Okay, if there's no more data, you'll still just get 0 as always. Okay, so that's how it's going to work. Let's see a couple examples of this. Let's talk about this little program called Slow Alphabet Server. I'm not going to type it up because of the time, but here's what it's going to do. We are going to artificially put some delay in here of a 0.1 second delay and a 1/10 of a second delay, which is noticeable. You can actually notice that. And what we're going to do is we are basically going to set up a client here we're going to have a thread pool like we've done before, right? And when we get a connection request, all we're going to do is set up a little output sock buffer and then feed the alphabet one letter at a time with a delay in there after each letter. Okay, so what that's going to mean, it's going to mean 26, it's going to take 26 letters, it's going to take 2.6 seconds to actually push out, which is really slow to push 26 letters out, but we're artificially doing this to see why it might be a good idea to use this non-blocking things. Okay, so here's what it does. Waits for a connection. It has a thread pool to actually handle the connection, so it can respond to many connections. The worker is slow because we put that artificial delay in there, and then it closes the connection. Nothing here is actually non-blocking, but it's definitely slow because we put that delay in there. Okay. You will see this often. Servers in general, if they're trying to serve many, many web pages, will give a little bit of data to you and a little bit of data to the next one and a little bit of data to the next one so that it doesn't block one for too long. Okay, and you'll notice this sometimes. If you're loading a web page, it loads partial data and it loads a little bit of the image you're trying to download, or it loads this ad and then this ad and whatever. It takes a little bit of time, and that's what happens. So you've seen this before. Okay, you've seen these. You've also seen buffering like on YouTube, which is more or less the same thing, where there's just not enough data that's gotten to you yet to actually give you an image or give you the video. So that's what happens there. Okay, so here's a client that we're going to actually test. Okay, and the client here has a while loop, and basically it goes and it tries to connect to the server, which is going to be on localhost here, the same machine here. And then it is going to read 1 byte at a time and then print out that byte. But we have yet to do this non-blocking thing. So the read, it's going to read it pretty fast, print it out pretty fast, and then go back here and read it again. The delay, though, is going to come from the server doing really slow pushing out of the data. Okay, and that's all it's doing. It's printing out this out. So let's actually see this. If we, let's see. There we go. Okay, so we have, what was the name of this file? This one was slow alphabet. If we do slow alphabet server like this in the background, and then we do, let's see, this one was blocking alphabet client. Okay, watch what happens. There's your amount of, like reading the 26 bytes. And you could tell it was slow. Let's actually time it. Okay, if you time it, then it will take, in this case, 2.6 seconds, which makes sense. We've delayed for 0.1 second for a letter, and it's 26 letters, and so forth. Okay, that shouldn't be too strange. Notice something in here. We did put a little, we counted how many times we called the read, right? We called it 26 times, mainly because we asked for one character at a time. Okay, is there a question over here?
Yeah, what is the double exclamation?
Oh, good question. Yeah, good question. So I used a little bash shortcut. If you do time exclamation, or do something with two exclamations, it does the previous command after, like, it does the previous command with time, for instance. So it just does the last thing. This would probably do it twice. Time. Yeah, it does the last thing with the current command. Good question. Okay, so anyway, that's what's happening with the server. Okay, nothing is new yet. Okay, we've basically done exactly what we've done before. Now, I could do this up to 128 times before anyone would actually not get 0.2 seconds, because I wouldn't even, I'd be able to keep doing this as many times as we wanted to. In fact, I'm going to cancel the server for right now. But that's, so that's where we kind of are already. Nothing should be new yet. Everything's blocking in the kind of the way it is. We put this strange delay in there to kind of show that it takes some time, and it could be a network connection that takes some time. Okay, question?
Why did you use like a while with reading instead of just using like a stream in the
Oh, good question. Why did they use the while loop? I kind of wanted to show you that you have to do it if you want to do it one byte at a time. If you wanted to do a stream, you could, but that's all hidden from you. And in this case, and by the way, it would ask for a big buffer's worth, so it would still wait 26 or probably 2.6 seconds, but not. It probably wouldn't. You wouldn't be able to see each letter. It would probably ask for the letter and then go, okay, or ask for the whole 26 at once. So in this case, you want to go, look, let's just see it one character at a time. Okay? All right. So this is what we just ran, and we saw that it took 2.6 seconds. And in our case, we're only reading one character at a time, so you can see each character, and you can kind of perceive that it's going to be relatively slow. Okay. So if we want to change to a non-blocking equivalent of this, we're going to use a function that we are going to see in a few minutes, and it's pretty low level, but it's just called set as non-blocking. So after you set up the client, okay, you call this function that plays some magic system calls itself and says, when you're reading from this socket, don't block on it. That's all it's doing. We'll see that in a little bit. Okay? But you're going to do basically the same thing here. When you read, though, okay, it is going to not block. So you could get a -1 back, okay, meaning that there was some error, but the error could be that it would just block. Okay, so you could do that. If you do get 0 back, it means that you're still getting or you don't have any data left, so that's fine, just like normal. But in this case, we want to, if we had greater than 0, we would handle it, and it should be just 1 byte because we're still only asking for 1 byte. And that's it. But the other option could be, what if it's -1? So it's not 0, it's not greater than 0, so it's -1. Check to see that it's not it would block, because that means there's some other error, the connection died, or there's some other error. But if it is, he would block, then you just go, all right, in this case, we're going to log that we had an unsuccessful read, and we just go and try again. Okay? This is going to do boom, 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 and try to read very fast. Yeah?
What's E again?
E again is I think E again and E would block are actually the same thing as it turns out. I'm not sure, they could be different on different systems, but here's how you would figure that out, by the way. You would say error no dash L, and that lists them all. Let's look at E would block. Grep E would block, grep E would, there it is, it's number 11. And in this case, E again, also 11. So it's actually redundant in this case, although on different systems it might not be. But either one of those could be the error number if it's going to block. E again means try again, basically. In this case, it happens to be the same number, so I guess it's redundant on our system. Good question. Yeah, good question. All right. So, question.
Why does the server set the client as non-blocking instead of the client setting itself as non-blocking?
This is the client, right? This is now the client they're doing. So the client now is setting it unblocking. Now we could set the server to also be non-blocking, and we'll see a little bit of that later. But we don't care right now that the server is blocking because it's still fast, and we've done it with a thread and whatever. But yeah, good question. Yep.
What's the advantage of doing this? Because you'll still be
Yeah.
wording the same amount of
Yeah, we have to get there. So this is a good question. The good question is, Wade, is there any advantage to this? We'll see an example later. Unfortunately, because of the time, I have to skip over some of the part that you can go look at the details. But we'll see why we could use we'll see why this is just another way to do a similar thing that we've already done. Is it better or not? Threads take a little time to spin up, and threads take multi-threading things. Letting the operating system handle the waiting is sometimes a better, like not the waiting, but the alerting us that there's data and so forth. Sometimes it's just a little more efficient. So new servers generally handle it the way we're going to talk about, just because they've decided that it's a little faster than doing the multi-threading. So this is really just another way of doing similar things we've already done. The way we've already done it, generally fine. But if you're going to serve billions of web pages, maybe you want to get a little more efficient. This might be a better way. The way we're going to show you is a little more efficient. So long answer for why we're doing it. It's another way to do it, or why is it important? Okay, so anyway, now if we run this is the non-blocking equivalent. Okay, if we run this and we do the let's see, we still need to set up the server. There's the server. And if we call non-blocking alphabet client, okay, it looks exactly the same, okay, but take a look at what just happened. We now got 26 bytes back, but we did, what is that? Let's see, 16 million reads in that 2.6 seconds, right? Well, why is that a good or a bad thing? During the time when we weren't doing those reads, we could have been doing other things. So let's say our program needed to do something else, right? We could have done that something else and then gone back and read again later. So otherwise, we would have had to block, right? This is a dumb way to do it because we're just chugging away and all we're doing is reads, but you'll argue that maybe you want to accept input from the user or something during that time instead of just blocking. Colin?
So the idea there is that this frees up time for threads to be doing work, or
this frees up time on the main thread in this case, right? Now, could you have a thread, could you have called that read in a thread? Sure. So it seems a little odd to do that, but you might do that. And then it's the same sort of thing. You might need to figure out when that thread ends and so forth. In this case, we're just saying, you know what, we're trying to read 26 bytes. Oh, it's going to take a while. Maybe we want to do something else in the meantime, right? I mean, what other things could we do? Non-blocking alphabet client, oops, not that one. How about non-blocking alphabet client.cc, right? If we do the read, this is the non-blocking read, okay? Let's say that we get to here where it was unsuccessful. Maybe we did something else, like I'm doing other work, right? Like that, and whoops. There we go. Make, and let's see, I don't think I killed the server yet, so that's that. There we go. It's doing other work, right? And you'll see there were letters in there. I don't know if you saw, but there were some letters interspersed in there, but look at how much work we did, you know? So you could have your one thread doing more work, and this is the way to do it. So that's the benefit. No threads necessary. in here. No thread pool, no threads necessary. We got the work done. We did have to re-ask a lot of times, but we were able to do more work. That's probably the bottom line.
That makes sense.
Yeah. Other questions on that? Okay. So where does that get us now? Well, now we've seen that we can actually do this. Okay, and we see that we get millions and millions of reads, and we got lots of extra time because 0.1 seconds to a computer is super duper fast. Okay, has anybody in here read the book Superintelligence by Nick Bostrom? One of my favorite books, although it scares me to death. It's a book about what happens when we end up creating a super intelligent AI that's actually smarter than humans. And there's lots of ramifications of that, and we have to maybe be a little careful about that if we want humans to actually persist. But one of the interesting things about that, they mention this, that computers are so fast that, if you're holding, and I think this is the example they use in the book, if you're holding a glass of water and you drop it, right? Well, because your neurons are relatively slow and the processing of the seeing things is slow, you don't get that much time to like move your hand down here and pick it up because you only see so many different data points. Now, the nice thing about your brain is it's very good at integrating. So if I throw a ball to you, your brain actually can see the path and put your hand in the right place. And you're very good at that. 2 billion years of evolution has done a good job of that, right? But a computer, your brain sees 100 or 1,000 different data points in the 0.1 seconds that it takes for something to drop. A computer will see billions or millions of data points. And so really, to a computer, dropping a glass is like, the glass is like, do, 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 do. And the computer's doing like, oh, I can do tons of calculations while it's doing that. And I can, so it's, that's the scary part, is that computers are just super duper fast, right, at that things. But they can't love. Not yet, anyway. Not yet. So anyway, read the book if you want. Like, it's a little bit of a scary book to read, but read it. It's good because it talks about some of the things, and especially if you're doing AI, it's just a great book to understand. Oh, we might have to face this someone in the future. But my point is, during the time when this is reading, waiting for that slow thing to happen, the computer gets to do zillions of other things, which is the point here. Okay, we could handle that in a thread, or we could do something, but now it's just one thread doing all the work. Okay, now here's the part that I'm actually going to skip over a little bit. There is this class that we are that is used in the other example that basically is going to be used to show you how you can do file reading or writing in this case piecemeal. Okay, and so it's basically it's just a little class that has an initialization that takes a file descriptor, and it takes the actual like data itself in a string format, and it's going to push that data to that file descriptor piecemeal, like some amount of data at a time. It's going to do that, and it's going to do that through this function called send more data. And if the send more data ever comes back with false, it means you're done sending data. But the whole reason for setting this up, and it's like many slides here showing you the nuances of this outbound file class, but the big idea is set it up so that you say, I need to send this string to this file and send some, and then it just continually can say send more data, and it will do that kind of on its own. And the whole point of this is doing that. So there are lots of slides here where it talks about the details here. Here would be a little test program for that, which basically sets up an outbound file, initializes it with it's actually a file name that gets read in, not the actual string, but it's the file name. It opens that file name up, and then in this case, it's going to print it out to standard out whenever you call send more data, and in this case, it's going to do that. Now, it does this in a non-blocking way. Okay, so it will send some data, and then it will send some more, and send some more, but it will try to return immediately. It won't try to send all of it. It might send 1 byte at a time, or it might send 100 bytes at a time, but it's some amount of data. So this is just kind of abstracting that away so that we can use it to show what happens when we do this with a server. So I'm going to skip over all the details about this. The basic idea, or the example here, takes a file and shoots it out to standard out. So I can actually show you what the end part of it is here. If let's see, this one is It is outbound file test, right? And it just prints it out to the file, but it did it in piecemeal, and you can't tell because there's no delays in this one. It just looks like cat, but in this case it does it. You just send one bit of data, one piece of the data at a time. That's all that's about. The details of this, you can go look at it. I don't think they're particularly important for getting through what we want to cover for the rest of the day here. So lots of this. Again, you have to deal with accept and so forth as part of this because you're trying to send to that outbound server. And let's see, we're going to just skip past this. Here's the, by the way, here's the set as non-blocking function. Okay, I said that it was low level. It's another one of these system calls that's got lots of stuff in it that you, if you want to actually use it, then you go do it. But the important part is here is that you call this function called fcntl. It takes in the descriptor and some other information, and you give it a parameter that says, hey, don't block on that descriptor when you're reading or writing from it. So that's all that's doing. There is set as blocking, which does the exact opposite, and then you can check to see if something is blocking or unblocking or non-blocking as well. Low-level functions, don't need to worry about those details unless you care about creating them. You can always just use that. Okay, so again, we're not going to worry about the outbound file abstraction. The idea is read a file. Every time you say send more data, send a little bit of chunk of data. That's all I care that you really know about. This is all blasting through that because of the time. But what I want to spend a little bit of time on is two servers that are going to utilize this outbound file class to actually enable you to serve data quickly without threads. Okay, so the same idea as we did before, or the same idea now is, oh, no more threads necessary, let's do it. Okay, we're going to use non-blocking I/O for a single threaded web server. Again, not necessarily the best way to do it, but probably a little more efficient than using threads because we can do that. Okay. It's going to be responsive because there's nothing blocking here, and it's also hopefully not going to miss any connections. Okay, that's because again, it's going to respond quickly, but then you're going to check many times to be able to check and make sure that you don't have a connection yet, and when you do, you get it and you handle it very quickly. Okay, so let's see some of the details here of this function. We are going to create a list of outbound files. In other words, what this server is going to do is you have a web page, and this is actually one that you can use from a web browser. I'll show it to you in action in a few minutes. But you're going to have a web page that basically is keeping a list of the files that you want to send out. So think of it like a web server saying, I'm going to go to google.com or I'm going to go to www.stanford.com and request a bunch of web pages. Each web page that gets sent back is going to be held in one of these outbound files that can get sent back piece by piece by piece. Okay, and we're going to keep a list of those in this program. Okay, so what's happening here? We are setting up a circuit. Okay, or a socket rather. We are then making it non-blocking. Now this is now the server is now doing the non-blocking part. Okay, it's going to set up this list of files that we're going to the connection files, the ones we want to send back. Turns out they're all the same file in this case, but we just because we're always just going to request the same file, we didn't say do a certain file, specific file. Remember in lab a couple weeks ago you did a file server. You remember that example? Hopefully you covered it in lab or you've looked it over. This is the same sort of thing, except now the file is all just one file. Basically the same basic idea. Okay, and then we've got a little bit of either logging or some other data capture thing. Okay, there's a while true loop in here. Okay, the while true loop will do an except, which will not block. Okay, and it will calculate, it'll just do the kind of the logging again of how many times it had to go through this while loop. Okay, if you don't have a connection, it basically just goes, if you don't have a connection, what we want to do is use the time now to send some data to all those files. So basically we're going to go, hey, does anybody want to talk to me? If not, I'm going to send a bunch of data to the files that have already been set up. That's all that's going on here. Okay, so we set up the, we send them out, and in here we are going to push onto the list of, if we do have a connection here, okay, then we are going to, if we don't have a connection here, we're going to this one it looks like we are doing it when we do have that. We're going to just get a connection, set it up, push it onto the data, and deal with it. If we don't, this is where we are going to send more data. Okay, so basically, you go and after you've tried to do a connection, if you set the connection up, great. If you don't set the connection up, then you push some more data to all your files, and just a little bit at a time, and that's all that we're doing. Yeah.
Can you go back a slide?
Yeah. I'll go back a slide.
What is the rationale between using accept versus create client socket?
This is a server, remember. This is the server going on here, right? So in this case, we're accepting somebody's requesting us, so we have to do the accept. This is basically where in every other program we've ever written, we've said accept, and it's just stayed right there until it gets a connection, right? Now it's going, oh great, I have more time to do something because nobody wants to talk to me, and what am I going to do? If I get a connection, I will set it up, right? If I don't get a connection, then or even if I do, the next thing I'm going to do is I'm going to take some time to push out to all those files that are requesting this data. And this is where it's going to, now, is this going to take some time? Yes. Now, if you have 1,000 files here that are being served, it is going to take some time. Now, by the way, we're getting into CPU-bound things. If your list has 10 or 100,000 different connections, now it's got to go whipping through this while loop 100,000 times. That's going to be CPU bound because none of those calls are blocking. It's just, I've got all this stuff to do. I have to do it in this case. So this is where it would become CPU bound. That's what's going on there. Okay. All right. Let's actually run this. If we run this, let's do it this way. If we run this, this one is called, let's see, hang on. I want to cancel the server before. This one's called the expensive server, okay? Let me just run it, and it's saying static file server listening on port 12345, and this is myth 61. By the way, I did restart all the myths today. I had to go and literally start half of them, and they were all just sitting there dead. I don't know why. 107 probably, not because of you guys. Let's do this. Let us go to myth, what did I say it was? Myth 61, and it is port 12345, 12345, and hopefully there is the file. So we are serving just this one file a million times, and it happens to be that. So if we go there and serve this file, we'll do that. Now, what's happening in here, and by the way, that was where it was doing that. If other people also wanted to connect, that might go up if two people are connecting at the same time, but it's going to go through pretty fast, okay? What's happening right now, this is myth 61. Let's check something. Let's see, SSH myth, let's see, Greg at myth 61. Yes, whoops, yes. And htop, we should, there we go. Take a look at what expensive server is doing right there. That 100% is my expensive server. Why? Why is my expensive server expensive? Right? Nobody's really requesting much data. And what's it doing? It is sitting here. Let's go back one slide. There we go. It's sitting here in this while loop, not blocking on accept. So it's doing this while loop again and again and again and again and again, and there's no data to serve. So this while loop is just going nuts. Okay, if we put a C out in there, we would see a whole bunch of C out statements, just like we did before. But what it means is that if we do htop, we are getting, there it is, 100% of the work is on one core, and some myth machine, myth 60, whatever this is right now the fans are starting to come on and whatever, and some poor 107 student doesn't get their heap allocator done or whatever. So that's what's happening there. So what do we want to do? We've got this feature. What did we do in the past when we had to deal with this? What did we do when we want to wait for something? Kyle?
We moved it off the processor.
We moved it off the processor, right? So we have to have, this is the same thing there, we have to have another operating system support for this, okay? And this is a thing called epoll, and the epoll family of system calls are basically waiting for file descriptors, okay? So it's basically saying, instead of doing that while loop again and again and again, and instead of blocking on it, we're going to we're basically going to go and call the function we want when something happens. So in other words, we're going to do some sort of waiting. If we have no data to send and we have nothing else going on, we are going to shut the processor down, or at least our process down, and we're going to do that. Okay, so there's a whole bunch of functions here. There's a create function that returns a file descriptor, and it has this clo exec thing, which we've used before, and it sets up a file descriptor that we will get alerted on, as it turns out. It has this watching facility, which basically says what's happening whenever something changes. So if you're watching a network connection, if data comes in, the waiting will stop. Okay, and you actually can call epoll wait to do the waiting around. Okay, and it's waiting until there's some timeout, which the timeout you can set so that you can go do more work and whatever. Okay, so it's basically the same sort of idea. You've just now have more control over it than you would have from a blocking sort of server. Okay, there's a struct in here. There's this interesting C thing called a union. Anybody know what a union is? You probably never used unions in C before. It's a pretty old concept, and it goes back to when data was scarce, like when you had data was scarce. Here's what this is, by the way. A union says this data structure can hold either something, a void star, or an int, or a uint32t, or a uint64t. And whichever one you happen to have in there, it will be able to get out that data based on which one of these variables that you use in there. So why does it do that? It's so that you can store different types of data in the same amount of space, right? It's going to allocate enough for the biggest thing, even though you might only be using a 4-byte int, right? It'll have enough space for a 64-byte int, but it won't. But it doesn't need to have a different one for each one. So it doesn't have to have 4 in there. It's just got 1. Go look up unions and why they're used. You don't see them too often, but when you do, you have to kind of understand what they do. Okay, we'll hold a single type of data out of a data types. Okay, what kind of events can we listen for? Okay, and this, by the way, this is now event-based things, and we've seen events before when we have signal handlers. That's an event-based model. But in this case, we can say for a file, the file is available for reading or it's available for writing. And we can also have it what's called edge triggered. And if you took CS107E, you would have heard of edge triggered before. But that means that you actually get like an event on a change in the descriptor, okay, versus what type of data you're looking for. This is saying, hey, I want to do it when I get the data. Okay, so what are we going to do? We are going to set this up now where we have the server itself. Main is not really going to change, okay, for this server. It's going to set up the socket, and with create server socket in this case, and then it is going to run this server. So this is just kind of abstracting it away, decomposing it a little bit. Okay, run server is going to set things as non-blocking. Okay, and then it sets this watch set of what we're blocking. It's going to build the watch set, which we'll see in a second, based on that server socket that we have. Okay, what's happening with the build initial watch set? We are setting up some epoll, in other words, to watch for that thing changing. Okay, and then there's some other. It's basically setting up the union and the struct there. In this case, the struct, and then it's calling this epoll control to set it up. Think of it in a very similar way to sig suspend. How you have to do the sig just have to set up the signals that you want to block and so forth. Same idea, different topic, but basically same exact idea. And again, I'm not asking you to memorize this stuff right now or know how to use it, but just know that it's possible to do this. Okay? All right. The next thing we're going to do is we are actually going to still do our while true. We're going to have these events. We are going to had the number of events get triggered by this wait thing here, okay? And we might have a timeout on there to say, just wait until there's a timeout so that we can go do data as well. You don't want to time it out, but it could time out, and if it does, well, it'll just go on and do the next part, okay? You can actually get many events triggered at exactly the same time. Think of it as the same thing as the child process getting a wait PID where it returns multiple things. So you should handle all the events here, okay? And when you get them triggered, we handle the events one at a time using a for loop. So basically, the events get triggered, we find those events, and then we go and deal with them, okay? And if you get an event, then you can actually, in this case, like consume the data, read from the file descriptor to say, hey, what did you want to tell me, right? And then it will do that. And then you can publish the response if you don't have things to read in, if you're just trying to write it out, okay? So what else is this? And there's a lot of code here. I know this is a lot of code that you have to do, but you have to see. But basically, we are setting up the accept. There's a new accept call, by the way, called accept for, which has this non-block parameter thing on there. Yeah, Mark, do you have a question? Oh, sorry. Go ahead, Amy.
Yeah, so I was wondering why this still counts as non-blocking.
Yeah, well, you'll see in a second why this is still non-blocking. It's not waiting in the same sense. It's basically you're doing it so that it's allowing. How should I put it? It's not going and blocking on the accept call. You're still doing that. It's just not going to have to call as many. It's not going to have to go through this loop as many times. You'll see when we get a little bit farther along. Good question on this. Okay. We have to do this. Is all set up and setting up the watch list and setting up the accept and so forth. Okay. So the consume available data part is where it's going to basically do the get the connection. Okay, and we're going to set the connection up. We're going to set the connection up at that point. Okay, and it is going to, and then we're also going to be able to do, that's just setting up the connection and getting the request. And then we are going to, let's see, do the, where is it here? We're going to, still take care of the requests, okay? And we may have a whole bunch of active connections, okay, that we have to do, and we've kept that in a map and so forth, okay? And then we will actually change the event based on whether or not we've already have connections. Again, these details, go look at the slides. I don't want to go into all the details about the how this works under the hood, but we basically are going to get requests or get the events happening, and the kernel is going to handle this for us, okay? So where do we get here? Publish response. This is where we're going to actually, in this case, we're going to do an actual website that we're going to respond with instead of that file in this case. And the publishing the response is going to, for all the different places that we need to send data, send a little bit of data at a time using the right command, okay? And it's only going to send, let's see, I believe it might, let's see, it's going to try to send, I think it actually tries to send all of it at once here, but that's that. And then after it sends all the data, it needs to close the client. Okay, where does that, like, what's the whole point? What's the whole point here? Okay, in this case, let's see, it's not blocking in the same sense. We've let the kernel handle the events for us. And in our case, we are still able to do the extra work that we want to while the kernel is waiting around for data to either come in or not. Okay, so it's not stopping us from handling this. But when there isn't any data to send or receive, we do shut down. We don't need to go back to that while loop. So in some sense, it's blocking in the sense that if there's nothing to be done, our process turns off. Right? But if we have anything to do, either sending or receiving data, it will be triggered by the fact that there is the kernel waiting, telling us, going, oh, you've got more stuff to send, go send it. You've got more stuff to receive, you've got a client connection coming in, do that. So the while loop will not just continue spinning like that. It will actually block in the sense, it'll block on more than one thing. And that's really the big idea, is that it's kind of blocking on both sending the data to all our different things. If there's no data to send, it will just wait around. Or if there's no accepting connections to accept. Does that make sense, Amy, to your why is it not blocking anymore? It's kind of blocking in the sense that it's not blocking, but it's basically saying now we can wait for two things at once, whether we have to send or receive, not just wait and check again and again and again to see if we have connections. So we're setting up these events to say, we've got two events, well, we've got at least one event, which is accepting clients, and depending on how many clients request the data, then we've got many more, we've got other things to do as well. Every time we are able to send that, the ePull will actually call the right function to do the work for us. So our main function can just sit there and we let the kernel tell us when to send and receive data. That's the big difference. So that's why it's not blocking anymore. We've leveraged the fact that the kernel will handle that waiting for us, and our main thread doesn't need to do anything. Could we do more work? Yeah, sure. We could continue to do more work, and now we're still waiting for two things at once. But it's just abstracting it away a little bit. That's all. And I know there's a lot going on here to see that. And the code, you can go and read through the code to do that. Here's the bottom line. Okay, the bottom line here is there are lots of ways to build a server. Okay, we've seen a number of different ways to do this. Okay, we can build a threaded server. We can build a non-threaded server and just kind of hope for the best. We can build a threaded server that uses threads or uses thread pool to do that, we do know that there are going to be some blocking calls, and it's fine to do that. Again, it's just maybe it's a different strategy to do that. But we've now seen another one where you let the kernel tell you when data needs to be sent or received, and then that'll work in a different way. Before I go on to more details, let me show you what this actually looks like. In this case, this is let's see, we've got the efficient server, I believe is what it is. It's going to listen on port 33333, and if we go to, what was it, Myth 61 again, Myth, there we go, 61, 33333, it's going to serve us this website, right? It happened to be a website where it tells that and went and pulled the image from somewhere and whatever. But you would be able to do that many times, and for every browser window that's open, it will just feed a bit at a time. And I think even if all of us in here tried to load that one page at the exact same time on our browsers, you probably wouldn't see much of a slowdown because it's just sending 1 or 2 bytes at a time, but doing it very fast to all of you. So that's how that's what's going on there. Okay, so where does that leave us in the big picture? When you're building a server, or when you're doing anything, and this is hopefully one of the big takeaways of this class, it depends on your own system setup. What operating system are you using? Maybe you're using an operating system that doesn't support this event-driven model. Well, too bad, right? Linux happens to support it, right? Maybe you have a computer that has a really fast network card and there's less waiting you're gonna have to do on that, or maybe it's got multiple network cards or whatever. What about the network itself? What if you're trying to serve a website through like your phone's data plan, right? You might have a totally different idea of the best way to do that based on the actual platform. So it's all about trade-offs, and it's all about how you can do that. The big idea with the server, accept and respond to as many connections as you can. That's the big idea, and respond as quickly as you can to client requests, okay? Don't block the accept, and don't serve too slowly. Those are the big ideas. And that's the basic idea of any server when you're setting it up, okay? You want to respond quickly, and you want to accept, and you don't want to block the user, okay? Don't write a server that busy waits, because we don't like busy waiting because it makes the fans on our computer turn on, right? We don't like that, and it just wasted CPU time and energy and so forth, okay? But you have to understand some of these low-level ideas. When you're making this choice, some of you will undoubtedly go to companies that do networking as their core business, right? Some of you might end up at Cisco or some other company that has lots of networking, right? That's happening or Amazon Web Services or something like that. And you'll have to understand some of this low-level stuff, right? Why do you avoid busy waiting and so forth? And do you need to know all the details, like all that stuff I just flew through? Well, it depends, but you will if you get into that. Take CS 144 if you want to do that. Okay? And you have to be smart about this too, by the way, right? This is a great comic. I love this comic because it's one of the XKCD comics that basically it's this server that says, "Hi, I'm a server." Have you ever done this where you go to a web page on your phone, and the server basically tries to give you the mobile version of the website, but it doesn't take you to the right page. It takes you to it's the main website, and then you're like, well, this is exactly what's going on here, right? Oh boy, can I help? Let me get it. Oh, you're a smartphone browser. Your browser tells the web server what kind of browser it is, by the way. And you can spoof it in some cases too. You can pretend that you're a regular computer browser even though you're on your phone. Sometimes that's a good way to do it. I don't know if the main browsers let you do that now, but they might. You have to sometimes you have to delete the M, but it's more than that actually. The reason the M shows up is because the browser, your phone's browser says, "Oh, I'm a phone," right? And the client or the server goes, "Oh, I better give you the pared down version," even though your phones have regular full browsers on them. So anyway, in this case, this server says, "Hey, I've got this new mobile version," and the phone goes, "Wait a minute, you're giving me the main page," and then the server just resets because it's kind of dumb like that. So build your servers smart if you're going to build servers, right? Don't try to be too fancy with them, even though you've got new things like browsers and your watch browsers and so forth. And there are trade-offs, but be smart about that, okay? All right, so we are a little early, which is great. As I said at the beginning of class, you guys made it through a difficult class. You can argue whether this class is more or less difficult than CS 107 or CS 103 or whatever, but if you weren't challenged by this class, you're a smarter person than me because this is, I think, a challenging class. You should give yourself a pat on the back for doing well and making it through all these crazy long assignments with 15 pages of reading and 100 files to look through and so forth. If you want to take more systems classes, there are tons of them. If this was the last systems class you ever did, well, you should congratulate yourself on being done with that too, and go do your AI stuff and whatever. And did I tell you about Chris Peach telling me that how important systems is to AI these days? And so Chris Peach, who many of you know, does AI research and CS education AI research, and he was talking with me the other day about the fact that all of the AI that's done now uses GPUs and TensorFlow and all these kind of systemsy things to do AI. And he says, I wish I paid more attention in 110 in those systems classes, or maybe I wish I'd taken a parallel processing course so I could dig in a little bit more to figure out what's going on, or at least I understood a little bit more about how this works. So systems is not something that you can do a lot of stuff without knowing much systems at all, but you can definitely inform what you're doing in almost any field by understanding a little bit more about some of the decisions that are made and so forth. So I'll leave you with that thought. You guys are great. Thank you for bearing with me during my first quarter teaching this all alone. I apologize if there were mistakes along the way, but you guys are great. I will see you on Monday at the final or during the office hours today and tomorrow, and thank you very much.